Hello, everybody. This is Mr. Yosef. I hope everybody's doing well. It's a beautiful day to watch a math video, so let's get started. So today, what we're going to review is factoring. So I'm going to make two separate videos, one about just a different type of factoring and the other just doing some examples. So one thing I just want to write first is what type of functions are we factoring? So we are factoring quadratics, which have a power of 2, or in this case, most of the times we're factoring something that looks like ax squared plus bx plus c. So this is called a trinomial, and it's quadratic because it's raised to the power of 2. So some students were asking about how do I know a difference between a perfect square trinomial and a perfect and a difference of squares. So just like the different types. I'm going to talk about that today. So first of all, we have our standard x squared plus 7x plus 12. So when we do this problem, the a value we say equals 1. So what I mean by a value is I mean the one in front over here. So this is 1. So whenever you have a problem like this, you know that this is your product and this number is your sum, and you want to go ahead and write your two parentheses. You know that x times x gives you x squared, and you want to think of two numbers that multiply to 12 and add to 7, and that is going to be 4 and 3. So this is the first type of example that I like to look at because this one gives me the most confidence and I feel comfortable with this one. So this is just a trinomial with an a value of 1. No tricks. You just need to know what's the product and what's the sum. So that is the first thing that we're going to look at. So now we're going to move on to something that looks like this. 2x squared plus 14x plus 24. What I want you to notice is that a does not equal 1. So I think about this in two different branches. You have when a is not equal to 1, you need to look for the greatest common factor first. So this might end up looking like something that we just did if we are able to factor out the a value. So when I look at this, I notice that I have 2, 14, and 24, and they're all divisible by 2. So I'm going to factor out a 2, and I end up with x squared plus 7x plus 12. So something cool about this is, I don't know if y'all noticed, but this is exactly the same problem that I just did up earlier, except this time I have a 2 in the front. And now I can factor the highlighted yellow part as x plus 4 and x plus 3. One thing that I see a lot of students do is they get happy right here. They're like, I'm done when I do that. And no, you're not done, unfortunately. So instead of being a sad face, it should be like a sideways face because you're in the middle. You need to check if you're able to factor and keep going. So as you can see in this case, you can keep going. Also, just wanting you to know that I am not picking like the hardest problems to do right now. I just want us to get more comfortable with what to look for. So this is factoring with a value does not equal 1. That involves GCF. So that's how I would label that one. So now let's go to a difference of squares. Right? Difference of squares. So this one should be the one that we should always recognize because there's only two terms. So you notice these are all different examples. So I can call this number 1, number 2, number 3. I want you to notice that they're all missing the bx. They're missing the bx. So I'm not going to do this all the time, but I like I told class, you can write this as 0x if you like, but it's not necessary because all of these have a certain pattern. But for now, let's just look at it like this. So you want to think of two numbers that multiply to negative 36, because this is the product, and add to 0, which is the sum. So y'all know that in order for the sum to be 0, you have to have the same number. Like it can't be two different numbers. So that's why I write 6 and 6, and that's why I write positive and negative. Because 6 minus 6 is 0, and 6 times negative 6 is negative 36. So what eventually happened is we notice a pattern. Anytime you have a difference of square, which means this is a difference of squares because it's raised to a second power, or if it's to the fourth power or sixth power, and these are perfect squares because you can rewrite them. Like 36, you can rewrite it as 6 squared. 81, you can rewrite it as 9 squared. So whenever it looks like this, the way that you do it, the general formula is like a squared minus b squared. If you think of a and b as being this, it's just a minus b, a plus b. And if I wrote this question as x squared minus 6 squared, where this is a and this is b, you have x minus 6, x plus 6. So this right here is just really technical, right? It seems more like you're trying to remember a formula, and I don't always talk about this because negative 36 is the product, 0 is the sum. You could always think about it without having to memorize something. But if you're like, what is a difference of square? Like, why do they keep using that phrasing? When can I use that? This is what it means if you're able to rewrite it in this form. So I'm going to do number 3, but I just want to make sure to show you that for x squared minus 36. Number 2, I forgot actually, is x squared minus 81. This is like x, and this is 9. So this is just x plus 9, x minus 9. Where you put the plus or minus doesn't matter because the a value is 1. So let's look at the last one, which is 2x squared minus 32. So some things that you should notice here is, first of all, 32 is not a perfect square because there's not two numbers that multiply to give you 32. So you can't write 32 like some number squared. And the same thing here, like what two same terms multiply to 2x squared? There's nothing there. So you can't jump into the formula or jump into the routine yet. You need to stop and you need to look at it and ask yourself the question that you should always ask first is there a greatest common factor? And in this case, yes, there is. So you factor out a 2, it becomes x squared minus 16. And now you're like, oh, x squared minus 16. That looks like the last problem that I did. So this one ends up being x minus 4 and x plus 4, because you could rewrite 16 as 4 to the power of 2. So what I call that is I call that a difference of perfect squares. Also, difference means subtraction. So you can't do like x squared plus 16. It has to be subtraction. All right. So now we're going to move on to perfect square trinomial. This is the one that gets me. I feel like it's not supposed to be confusing, but it just feels like something you just have to memorize. So, first of all, let me just show you how it looks like. A perfect square trinomial is something, I'm going to give you an answer instead of showing you what it looks like first. Something like this, or something like this. These are both factored forms of perfect square trinomials. So I'm going to factor them out, and I want you to think about why they're called perfect square trinomials. So if I did this one and distributed, you get x squared plus 14x plus 49. Do you guys notice that 49 is a perfect square, which is 7 times 7, and 7 plus 7 happens to give you 14. That's why we call this a perfect square trinomial. It's because the product is a perfect square, and when you add those two numbers, it gives you the b value. And same thing if we do this bottom one, you get x squared minus 12x plus 36. So once again, same idea. The two numbers that multiply to 36, 6 times 6. And remember, there's two ways to multiply to a 36. It's either 6 times 6 or -6 times -6. And as you can see, -6 minus 6 also gives you -12. So that's why these two examples are called perfect squares, just because the last number is a perfect square, and when you add or subtract those numbers, it gives you the middle term. So does this mean that every time you see a perfect square at the end, you're always going to do this? No. There's a lot of examples where this is not true. So for instance, if I gave you the example x squared plus 21x minus 100, you're not going to be like, oh, that's 100. So Mr. Yosef said 10 times 10, but 10 plus 10 doesn't give me 21. That's okay, because this problem is not a perfect square trinomial. If you actually factor this question, this one ends up being x plus 25 and x minus 4. So it's just something that you can notice. It's something that can be a shortcut in these problems above, but you can still do the same thing you've always done. You can still ask yourself what two numbers multiply to 49 and add to 14, what two numbers multiply to 36 and add to -12, and you happen to see something cool where both of them end up being the same number to give you the sum. So that is what a perfect square trinomial is. And the last example that we have not talked about is an a value that's not 1 that does not involve GCF. So let's do one that's a little more challenging. So let me find a question. I think I have one. I want to make sure to find an example that doesn't have a GCF. So something like this: 15x squared plus 14x plus 3. So this is the procedure I've always done. I've always noticed product, sum, and I noticed this time that A is does not equal 1. So I know somehow that my A values are going to affect this process of factoring. So when I write my two parentheses, which I normally do confidently, I can either write 5x and 3x or 15x and x. I want you to notice that we didn't have this dilemma earlier because what two terms multiply to x squared? It's only x times x. Even on this one earlier with the GCF, I think it was this one right here, when we ended up taking out the 2, we ended up having an a value of 1 again, so we didn't have to worry about it. But this is the first time where the a value is still there and it's greater than 1. So I always tell you, when you do this, you have to be, what's the word? You just have to be observant of what's going on. So our product is 3. So when I think about what two numbers multiply to 3, it's only 3 and 1. So I would write product, I would write 3, and I would write 3 times 1. And I want my sum to be 14. Well, I know that 3 plus 1 doesn't give me 14 because this times whatever number I choose there, if it's 3 or 1, and this number times 3, I know that these two are the ones that are going to end up adding together to give me the 14 that I want inside. You can also say the same thing about 15 times this number and this number with that. But I want you guys to think about something on the bottom. 15 is a big number. So if I put 15 times anything, even if this is a 1 or a 3, let's say I put a 1, that's 15x. Let's say I put a 3, that's 3x. 15x plus 3x gives me 18x. So that is too big. So I just know that most likely this bottom one is not going to be correct, that it's going to be the one on the top. So is this going to be a 3 or a 1? Same thing here. If you put a 3 here, you're going to get a 15. And if you put a 1 here, you're going to get a 3x. Too big, because 15x plus 3x gives you 18x. So all I'm going to do in this problem, so I'm going to switch the orders and see if that helps. So let's put a 1 here, and let's put a 3 here. And 5 times 1, 5x. 3 times 3, 9x, 5x plus 9x equals 14x. So this one works. So, sorry, the x got erased, so it should have been this. It should be 5x plus 3 times 3x plus 1. So that would be my answer for this one. So once again, it's a lot of work there. It's a little messy, but I will do more examples and I'll do them slower. But this video is to try to introduce you to all the different types of factoring that you will encounter on this test. Thank you.